Good evening, everyone. Welcome to our ninth weekly discussion session for the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, Indian Institute of Technology. So, today's session will be a direct continuation of what was discussed last week. So, we shall be starting our discussion, or rather, our entire discussion is going to be about MOSFET characteristics. So, when I say MOSFET characteristics, I'm primarily referring to characteristics in the linear and the saturation regime. So, these are the only places that we are concerned with, because last week more or less we established what are the conditions required for a MOSFET to move from the cutoff regime to the active regime. So now we shall be concerning ourselves with the linear regime, which is the active regime. I mean, technically both linear and the saturation regime are active regimes because the device is allowing current to pass through it. So in the active regime, we are looking at the linear and the saturation behavior of the MOSFET. So our idea will be to understand the notion of channel electric field, and then uh, the linear and saturation currents, and through this also get an idea of what is the classical pinch off, like the channel pinch off, which leads to the saturation behavior. So channel pinch off is the cause of current saturation. So that is that. And we shall conclude our discussion with a brief look at the thermal velocity in a ballistic channel. So this is an important quantity which will determine, like, essentially this will be the average velocity of an electron in a ballistic channel, and with this we can make several qualitative estimations on the voltage current relationships, or many other properties of the device. So moving on. For our discussion, we shall be using the following direction conventions. So the MOSFET device, so here we are only looking at an N-channel MOSFET, will be when represented like this, the cross section. What we shall see is that the x-axis goes along the channel, so this is along the channel, and the y-axis goes transverse to the channel. So whenever I say transverse, I imply the y-axis. All our analysis, of course, since we are concerned with IDS, any lateral movement of the charges from the source to the drain goes along the x represented by the x-axis. So the channel length, the complete length of the channel, or rather to be more precise, the length between the source and drain, no, I shouldn't put it like that. The region under the influence of the gate voltage, yes, that is a more precise way to state this. The region under the influence of the gate voltage is the total channel length. So that will be given by L. We will see how this quantity varies as the device operates in different regimes, and the flow of current is as indicated. And since we are in the active regime, we are guaranteed that VGS is greater than VT, which is the activation condition for the N-channel MOSFET. So similarly, now to give a uh, what to say, like, idea of what channel pinch off is that under certain conditions, we'll see what those conditions are. What will essentially happen is that this inversion layer that is formed, essentially this electron rich layer that is formed due to the applied gate substrate voltage, will now begin thinning as we move from the source to the drain. So because of this, the availability of charge carriers, as we are free charge carriers, as we are going closer and closer towards the drain, becomes lesser. And due to this fact, and additionally, since there are no charges here, it also implies that there is no electric field here. So that can be seen from, say, using something like Gauss law. Essentially, any electric field in this region will be related to the free charges present over there. So since there are no free charges present over here, the electric field in this region will be zero. Since the electric field is zero, this implies there is nothing accelerating the electrons at this point. Therefore, whatever velocity the electrons had at the point just before the pinch off point will be what will be the velocity they have as they enter the drain, which implies the current will be like capped at that value. Increasing VDS any further will not increase the IDS substantially. So in the pinched off region, I will write it right here. In fact, I will use a different color so that it becomes emphasized. What I can say is the electric field Ex becomes 0. So this is to be understood. Okay, so that is the first notion. So we shall be looking at these two regimes of operation of the MOSFET. And most of today's analysis is going to be, not most, almost all of today's analysis is going to be in the classical regime. Although a brief introduction to the Landauer transport model in MOSFETs has been given in this week's lectures, I shall be covering it in the next week because questions pertaining to that are present in the assignment for week 10. So the topics have been organized in this fashion so that it would aid in solving the assignment of the upcoming week, which is week 9. Okay, so this is an expression we have known from last week. So the drain source current is given by the channel width multiplied by the magnitude of charges stored in the channel multiplied by the average velocity. So this is the current flowing through the channel. Now, here one can ask, why am I only multiplying with channel width? Because I'm looking at the classical scenario, and some people may ask, why is this not, say, what happened? Yes. So why is this expression not the area of cross section? Why am I writing it just as the channel width? The reason for that should be apparent from this figure itself. The actual region where current carriers are present is actually a very thin slice in the substrate. That is the small inversion layer. It's not even an inversion region. That's why we call it an inversion layer. It is so thin that if the electric field, or rather the applied voltage, increases beyond a certain point, then we kind of lose that layer. So for all intents and purposes, even in a 3D MOSFET, like in a bulk MOSFET, the area which leads to current carrying, which contains the current carrying charges, the mobile charges, is effectively two-dimensional. So this is actually a quasi 2D space. So the channel here, I can even mark it over here and say that this is the, in fact I will take it the other way around. I would say this is a quasi 2D channel. So this must have been discussed in the lectures as well, but this is not very clear. I have to, yes. So yes, so this channel is a quasi 2D channel, and that is the reason why we are just multiplying the current expression with the width of the channel. So this is for clarity, so that there is no confusion over there. And in the linear regime, which is defined by a small VDS, the drain source voltage, we can say effectively that since VDS is small, the charge in the channel, the charge density in the channel depends only on the gate voltage and the offset capacitance. And that relation can be written like this. Of course, we need our charge carrier concentration to be inverted, which will occur only above the threshold voltage. Therefore, the charge in the channel is given by the offset capacitance multiplied by VGS minus VT. So this is the standard capacitance model. So this essentially comes from the theory of MOS capacitors. So this is again something many of you may be familiar with in previous relevant coursework. So anybody who has studied basic semiconductor devices will know that the charge that is present in the channel is essentially, the charge accumulated in this structure, that is the mass capacitor. Essentially the y-axis orientation of, just 1 second. I think I chose the right color. I got confused for a second. Yes. So if I say this is the metal, so this is the metal, and we say this is the oxide. So I will say shade it black. If I turn it to this, and I will say yes, this is the oxide. And we have the substrate below that. So we have a substrate layer below that. So any charge that is accumulating over here due to a voltage applied at this point, Vg, essentially it is going to be like VGS. So I have a Vs here also. Again, as mentioned before, yeah, I should write it like this. I should say yes. So Vs. Typically, this and the source have the same voltage. Right now, there are no source and drain contacts. So this is the substrate. So it can be treated as a capacitance, where I have a voltage applied across these two, and the oxide in the middle plays the role of the dielectric. So this is a parallel plate capacitor. So the capacitance Cox will be equal to epsilon R epsilon naught into A oxide divided by T oxide, or rather T ox. Okay, so this is epsilon A by, so this is the oxide thickness. So this is T ox, and we have A ox is the cross-sectional area of the metal. Like typically the metal and oxide have the same area of cross-section. So we have this kind of a an arrangement. Yeah, I forgot to write Vg over here. So just 1 second. Yeah. So yes, I seem to be having some internet connectivity issues. Hopefully it will get sorted out. Yeah. Yes. So the yes. So this is the capacitance of this metal oxide semiconductor like stack. So this mass capacitor. So the charge stored in the channel can be roughly said that it is the charge accumulated in this mass capacitor, and because of that we have this expression over here. Now Cox can be written like this. Um, so this will give us the charge. In order to obtain the velocity, in the classical, yes, so I should be more precise here. This is the classical velocity, because the average velocity for the ballistic channel, where we do our semi-classical derivation, will be different, which we shall be doing at the end of today's session. So that will be given by minus mu n dV by dx, where mu n is the electron mobility. So this is the electron mobility, and minus dV by dx is essentially the electric field. So minus dV by dx is the, to be more precise, this is the lateral electric field. So we shall call that, say, Ex. Yeah, I should have been more careful here because I've used the same epsilon symbol for electric field and the permittivity. So yeah, I will write this as epsilon naught, yes, and epsilon r, yes. So epsilon r is the dielectric constant, and this is the permittivity of free space. This is a known constant. So this is the lateral electric field. So in a linear channel, we have a small BTS. So since it is small, we can say that the lateral electric field epsilon, or rather Ex, is approximately equal to VDS by L. I mean, it's technically minus VDS by L, but again, like only the magnitude is required here because we are trying to find out the magnitude of the current. So we'll just say the electric field. Since I'm dropping the sign, I'm not like effectively I'm not mentioning which direction the electric field is pointing in. But of course, we know in which direction it is pointing in. Like typically, as the electric field, as the potential drops, the electric field increases in the direction in which the potential is dropping. Okay, so this is the value of the electric field in the channel, the lateral electric field. Therefore, in the linear regime, average velocity will be mu n times VDS by N. Okay, so these are the main features. So you can just substitute all the relevant quantities up here, and therefore we will get a final current expression, which I'm just going to write right below this. So it can be written as W by L into Cox into mu n into VGS minus VT multiplied by VDS. So this is how the current varies in the linear regime. And this is an expression you will find in the lecture slides as well. So, sorry. Yeah. So, yeah. Moving on to our first problem. What we've been given is a long channel MOSFET with channel length of 1 micrometer. So this is like significantly longer compared to our previous examples where we had channel length in the nanometers. So this is like hundreds, if not thousands of times longer than that. So, and width of 10 micrometers with an oxide capacitance of 3.45 into 10 to the power minus 7 uh, farad per centimeter square. So this is important. Here the capacitance is given per unit area. So please keep this in mind. Over here, this is just farad. So I hope you can figure out which quantity is missing in the expression given here. However, I shall be explicitly mentioning which is missing. So let me see if I can use a different color here for today's problem solving thing. Would yellow look good? Yeah, yellow looks reasonably okay. So yes, so we have now calculate the charge density in the channel if the threshold voltage is 0.7 volts and VGS is 5 volts. So these are the parameters that are given to us. So first we have to understand that we have been asked to find the charge density. So how do we find the charge density? Charge density is, so in this case we shall write our Surface charge, again, as mentioned previously, the charge density here will be a surface charge density. So that should be understood first and foremost. So when I say this is a surface charge density. Okay, because we are looking at an inversion layer. So sigma will be equal to Q divided by A. Therefore, which implies sigma is equal to Cox into VGS minus VT divided by A. And this is this quantity right here is capacitance per unit area, which is what is given to us. Of course, it has been given in terms of uh, farad per centimeter squared. So we should remember that the corresponding charge density will also be in per centimeter square units. Okay, so that is the like idea here. So even though the length and the width are given, we need not use those quantities. Conversely, one could have simply just multiplied the oxide capacitance by the area of the channel, which will be like length into width, and then get the total capacitance and then do the calculation and then divide by, in this case, it will be 10 micrometers squared. But that is not required. So this quantities here were essentially misleading. Had this been a test question, well, it would have been a trick. Of course, I did not consider that. Consider the fact that I would be solving this question myself. So with this, all we have to do is just multiply this capacitance by VGS minus VT. So that is going to be 3.45. Oops, got to change color. Yes. Therefore, sigma is equal to 3.45 into 5 into 5 minus 0.7 will be 4.3. So this is going to be approximately, of course, this is 10 to the power minus 7, so this is going to be approximately uh, what was I thinking? Yes, 1.5 into 10 to the power minus 6 coulomb per centimeter square or square centimeter. So this is the surface charge density in the channel. So the calculation is as straightforward as this. So for any other assignment question or example that you might come across, the same process needs to be followed. Of course, pay attention to the unit of capacitance that has been given. Is the complete capacitance given or is the capacitance per unit area given? And based on that, remember to multiply or divide by the appropriate factor. Okay, so now moving on to the second question. So here what we need to do is calculate the current flowing through this channel if the drain source voltage is given to be 1 volt and the mobility is 800 square centimeter per volt second. So this is the unit for mobility. So this this unit can essentially be seen as uh, like centimeter per second divided by volt per centimeter. So like volt per centimeter is going to be the unit of the electric field because that's dV by dx, and centimeter per second is the velocity. So this thing is essentially given in the CGS units. Okay, so it's technically not CGS, it's mixed units because we are also using volt and not stat volt. So yeah, sorry about that brief digression. So yes, again going back to our original current expression. Why is the slide? Yes. So far what we've done is we've done these two. We've done Cox into VGS minus VT. That quantity we already know. All we have to do is multiply by the the mobility, VDS and W by L. So we know that W by L is 10, so IDS is equal to 10 into our Cox into VGS minus VT is 1.5 into 10 to the power minus 6 into VDS, or rather let me multiply by the mobility first, so that is 800 centimeter square volt second. Oh, I don't have to write the units because I'm just calculating. So again, this is per centimeter square, which is why these two will kind of get cancelled out. Okay, so and finally we have yes, the voltage, which is 1. So this is going to be 800 into 10, which will be 8,000. 8,000 into 1.5 is going to be 12,000. So that is like 3 by 2. So 12,000 into 10 to the power minus 6. So that is going to be 12 into 10 to the power minus 3. All the CGS units, like all the centimeters, have cancelled each other out. So all I have to write is this is coulomb per second or amperes. Therefore, IDS is equal to 12 milliamperes. So this is the current flowing through the channel at this given value of VDS. So calculations again are pretty straightforward. Now moving on to the saturation regime. So in the saturation regime, what happens is the current ITS becomes more or less constant. Like it is not going to become completely flat. If you remember from our previous, okay, yes. So if you remember from our previous session, then if you are looking at the IDS versus uh, VDS curve, which is the output characteristics, then what you will have is something like this. You'll have the linear regime, and then the current will become more or less flat. So this is for different values of VGS. So, and the saturation point is roughly occurring at the same voltage. This kind of starts shifting. That is due to the fact that there is DIPL. So ideally speaking, again, saturation will trigger at the same exact voltage in an ideal system. So this is the IDS versus VDS curve. Okay. So at even lower voltages, it's going to be like this. So yeah, and the line is kind of bending here. Of course, I hope you understand that. Okay. So this is what is happening. So when I say more or less constant, what I mean is the linear increase is kind of replaced by the a sublinear increase. It is no longer increasing linearly. In fact, it is increasing slower. Okay. So with respect to increases in VDS. Now this is caused due to the pinch off in the channel. Pinch off I had described previously, I mean when I was talking about it in the first slide. So essentially what is happening is the electric field in the channel drops to 0 at a certain point. Since it is dropping to 0, the velocity is not increasing any further beyond that point. Okay, so because of that, what we can say is like essentially, if I have my, I'm quickly switching to our two-channel device diagram. Although this is not two-terminal, I should say two-channel. Sorry. So I have my source and my drain, and in fact, I shouldn't have done that at all. Yes. So I have the substrate also. And now on top of this, there is the gate electrode. Now this is not an accurate representation of a transistor. I'm merely trying to like give an idea. So as the drain source voltage keeps increasing, the inversion layer that is formed in this channel will slowly start like thinning out. So for small enough voltages, it will be roughly constant. So it's going to be roughly a constant thickness. However, if the voltage becomes VDS becomes high enough, what we will have is something like this. So the inversion layer will kind of get pinched off over here. So instead of having the full length of the channel L, what we will have is, so this is L, what we will have is this length over here, which is given by L dash. So this is the L dash that I'm referring to, which is why I'm saying the inverted channel length is reducing. It does not mean that the device is shrinking. Please don't take away that message. I'm not implying that at all. I mean, outside of like mechanical stresses or like very high temperature changes, the channel length is not going to vary by that much. I mean, in fact, for all intents and purposes, we can assume that the channel length is never going to vary in a device, because if that is happening, probably the device itself is reaching some kind of a breaking point. Okay, so the saturation current, again classical, is given by W by 2L dash, where this is the new like shortened pinched off channel length multiplied by mu n into offset capacitance into VGS minus VT, the whole square. So this is the expression. Now as you can see, in the ideal classical case, this no longer depends on VDS, and therefore our like current is kind of becoming flat. Of course, that doesn't happen because we have effects like DIBL, where increasing the drain voltage keeps lowering the barrier. So some extra current, some like electric field does, transverse electric field does remain in the device. Ideally speaking, we don't want that because we want a clear distinction between these three regions. Like in the saturation region, we want the current to stay saturated and not increase beyond the saturation point. So we want it to remain constant, but however, in a realistic device, that does not happen. Okay, so this is the ideal case, also to be remembered. So this is the ideal case. So we are not considering the non-ideal realistic effects. In a manner of speaking, we shall consider them later. Okay, so now moving on to our next problem. So first what we have to do is we have to derive an expression for the saturation current in the MOSFET. Again, classical saturation current. So let me say this is the classical saturation current. Now, why am I doing this derivation? This kind of will cover all the relevant concepts that we need to understand in order to solve the assignment questions for this week. Okay, so let me switch back to the new color choice of this week. So what we have to go back to and remember is this. We'll be using this expression. IDS is given by W into. So at any given point, the, yes, so let me just write that first. So Cox into, there's going to be some voltage expression here, and then we are going to have the mobility into dV by dx. So this is kind of what's going to be, not this is not kind of, this is going to be the expression for the current. Now what goes in here, like what is the factor, like what is the voltage term that is going to appear in this expression? Now what we have to remember is when we have a MOSFET, so when we have a classical like bulk MOSFET, so yeah, I should have had multiple copies of the MOSFET diagram. Yeah, I'm kind of like inverting the thing. I think the figure given in the slides is blue substrate and red channel. So here I'm kind of reversing the thing. And we have the uh, oxide and the So this is the oxide layer, and we finally will have the just use the black metal on top of the whole thing. So this is the gate. So this is the gate. So we have no arrows. So we have VGS greater than VT. So yes. So now we are considering the case where the channel is getting pinched off. So this is the pinch off point. Now this pinch off is occurring, as I told before, due to the increase in VDS. So what we can directly assume is that VDS is lowering the potential, because introducing a voltage here kind of lowers the energy level for the electron, like lowers the energy for the electron in the drain, which is why there is a flow of electron from the source to the drain. Now this lowering effect, of course, will not be localized strictly to the drain. It will also spread out into the channel. So when that happens, what we can simply say is the voltage that a point in the channel experiences here is no longer just VGS minus VT, but it is VGS minus VT minus the voltage in the channel due to the applied VDS. So this is the general expression for the current. In fact, this is the more precise expression for the current. Okay. Oh, no wonder. So, like, yes. I was wondering why things got really thin. So we have VGS minus VT minus V of X. So we have this kind of an expression here. Okay. So now to go further with our derivation, we are going to assume two things. First, we are going to assume mu n is a constant across the channel. This is actually not true, because mobility depends on the environment in which the electrons are present. So it will actually depend upon the local potential also. However, we are assuming that this is constant for the sake of simplicity. Again, just to get a feel for the results. Okay, so this is, and additionally, we will also assume that IDS is also constant, which implies the current does not vary as it is flowing from source to drain. This is a reasonably good assumption for relatively shorter channels. However, in longer channels, this assumption will not hold. And since we are more concerned with short channel devices, I mean, that is the whole central thrust of this course, we can actually be more or less, like we can accept this assumption more easily, is constant through the channel. So these two things are true. This implies that whatever current enters the channel is going to be the current that is moving out. So from that, what we can essentially say is the following. So we can say that, ouch, yeah, sorry. The current that is at, okay, so if you go back to, let me just go back to the figure here. Oh, no, this one here. So remember that x equal to 0 starts from the beginning of the channel. Essentially, it starts just to the right of the source. Okay, so that is where our x equal to 0 point starts. So wherever we have our inversion region, the beginning of that marks x equal to 0. So from there, going to x equal to L will give us the length of the channel. Okay, so yeah, now continuing with our derivation. which implies the current at Vdx equal to 0 is uh, going to be not Vdx, Vx equal to 0 will be the current throughout the channel. So what we will simply say is we will now substitute the value of, like, the approximation that we are doing is I'm going to take this current expression, replace L by L dash, and uh, keep everything else the same. So if this device were to behave in the linear regime, then this would have been the uh, this would have kind of been the current flowing through the channel. So what we are going to do is we are going to keep this kind of constant, and then oh no, wait, just one second. I actually don't have to do that. I don't need the second assumption. The only two assumptions required are these. So from here, I can actually directly integrate. Okay, so IDS integral, yes. Oh yes, I'm assuming it to be constant. Therefore, IDS will jump out of this integral, like it will be left out. So from 0 to L dash dx is equal to W into Cox into mu n times integral this whole quantity, which I shall now write as Vgs minus Vt minus V of x dv. Okay. Now, again, this integral needs to be done from. So essentially, yes, the actual assumption is here I have to mention that V of x is 0. Yes. So this is our 0 reference level. Okay. So 0 to Vx, or rather VL dash in this case. Okay. So from that, what we will get is I ds is equal to, or to be more precise, it won't be V of x. Since we have applied VDS, the maximum voltage it can achieve is VDS. Okay, so now this is going to be W by L dash into Cox into mu n times VGS minus VT into VDS minus VDS squared by 2. Yeah, so this is the current in the channel. Now, the lowest, I shouldn't say lowest, the current beyond the pinch off region, essentially as it crosses this point, what we have to understand is the voltage will kind of drop to 0 at that place. So at the pinch off point, as I mentioned, the electric field will go to 0. So will the potential, because as long as I'm having a the potential kind of becomes constant. So we set the reference line here at 0. So at this point, V of x will be VGS minus VT. Okay. So from that, what we will get is, so this will become VGS minus VT the whole square. This will become VGS minus VT the whole square by 2. Therefore, this implies ID sat is W by 2 L dash Cox mu n into VGS minus VT the whole square. So this is the expression that we had in the previous slide. Okay, so this is the saturation current. Now problem 4 is, using the parameters given in problems 1 and 2, find the minimum possible value the saturation current can have in this channel. So essentially what we are asking is, as you can see here, for different values of VGS, the saturation current actually takes different values. The question that is asked is what is the minimum possible value it can have for, say, VGS is equal to 5 volts. Okay, we have not been given what VDS is, of course, because VDS needs to vary. Okay, so use the relevant, yeah, I should have mentioned using the relevant parameters. One should not take VDS is equal to 1. So I will again, like while I'm solving the problem, I will show what values I'm taking. So now, what is the minimum possible value the saturation current can have? So how do we go about it? For that, we have to look at this expression. So in this, assuming all other parameters are like, let me say VGS is fixed. If VGS is fixed, then everything else is a constant associated with the device. The only variable is L dash. It is a question of where the pinch off is occurring. Now, where the pinch off is occurring is strictly dependent on the drain source voltage. So the higher the drain source voltage, the sooner the pinch off will occur. If it is very small, then there will be no pinch off. We will have a continuous channel from source to drain. However, as it becomes higher and higher and higher, the pinch off will occur sooner and sooner and sooner, which implies a higher, like our expectation will be that IDSAT will keep going higher, which kind of makes sense because to make the pinch off occur sooner, we need to apply a higher drain source voltage, which implies the transverse electric field in the channel region is actually becoming larger and larger and larger. Okay, so the only quantity that is varying in this case is L. Okay, so what we have to remember here is IDSAT is minimum if L dash is maximum. Okay, so that implies, and L dash cannot be greater than or equal to cannot be greater than L. So L dash is always not. This implies, so since L dash is always less than or equal to L dash, or rather max of L dash, let me just max of L dash is equal to N. It cannot be anything larger than that. So the minimum possible IDSAT will be simply given by, at a given VGS. So IDSAT, let me say this is, yeah, let me put it as a superscript. So minimum IDSAT will be given by W by 2N into Cox into mu N into VGS minus VT whole square. So now this is going to be 10 divided by 2. The units cancel each other out into 3.45 into 800 into 4.3 whole square. So we already know 4.3 into this is 1.5. So what I'm simply going to do is I'm just going to say 1.5 is 3 by 2. So I will say this is 30 by 4 into 800 into 4.3. So that's going to be just 1 second. Yes, of course, the powers of 10 should be remembered. So this whole thing, this is going to be 10 to the power minus 7. So a factor of 10 to the power minus 7 should be remembered here. 7. So 10 to the power minus 7. Everything else is the same. So now this will come out to be, okay, I think I have to insert a new slide. Let's is equal to yeah. So the product of all of this will come out to be 25,800. So this is 25800 into 10 to the power minus 7 ampere, which will come out to be 2.58 into 10 to the power minus 3 ampere, which is equal to 2.58 milliampere. So this is the lowest possible value. So any saturation current, like realistic saturation current in the device, is going to be much larger, not much larger, it's going to be larger than this. So this is the lowest possible value the saturation current can have at the given gate voltage. So in order to reduce the saturation voltage further and further and further, we actually have to bring down VGS. Which again makes sense, because by bringing down VGS, we are reducing the charge carrier concentration in the carrier concentration in the channel, in the inversion region. Okay, so this is the minimum ID sat. Conversely, what one could have done is, so let me quickly give like problem 4.1. So, which, yes, why not? So now, if ID sat is equal to, let me say, 3 milliampere, then find out where the pinch off has occurred. Oh, oops. So now this again is what we have to do is we have to say 3 is equal to W by 2L dash into Cox into mu n into VGS minus VT whole squared. Now again, since L was 1, all I can like simply say is like I can just take the L dash over here and bring 3 over here, because like for L dash equal to 1, I know the value here, which implies the actual L dash is equal to whatever current value we calculated here, which is 2.58 divided by 3, which is going to be so this is going to be 0.86 micrometer. So essentially, not essentially, so over here, this is the kind of scenario. If this whole thing was 1 micrometer, 1 micron, then at 0.86 or rather 860 nanometers, the channel has achieved pinch off. Okay, so that is how it is. So now one can ask a further question to this. Like I'm essentially adding questions on top of this question. So now let me say I'm going to do give another question on top of this. So let me just insert a new slide. Yes. The next question is for the previous case, that is ID sat is equal to 3 milliampere. Guess, or rather I shouldn't say guess, estimate the value of VDS. Now this is kind of like, this is where we need to use some of the assumptions that I was stating in the derivation. So now how do we estimate the value of VDS given that ID sat is this? So first what we have to do is we have to, of course, guess where the pinch off has occurred. Now what we should remember is at the pinch off point, Vx is equal to, so let me write this here, and this is important, this needs to be remembered. Okay, so at pinch off point, V of x is equal to Vgs minus Vt. So this is true in any case. Like when pinch off occurs, this has to happen. If this never happens in the channel, then no pinch off has happened. And our device is working more or less in the linear regime. Okay. And now what we are also going to say is we are going to, since this is a long channel device, we have an assumption. So our assumption is this. I mean, people may have already guessed it. The assumption is simply that potential is very, oops, linearly through the channel. This implies so what does this imply? This implies that electric field X is constant in the channel. And this is kind of an important assumption which you will see in next week's lectures, and we shall discuss it in detail, like why this should be constant, what will happen if the electric field starts to vary, and that is directly related to many of the non-ideal behaviors we might come across in a MOSFET. Okay, so this is an assumption. Now, since this is the case, what I know for a fact is, uh, so the electric field now, Ex will be Vds by L. So this is the total electric field across the channel, because that is the potential difference divided by the length. Now, since this is constant, this implies Vds, this is also equal to Vds minus, I can simply write it as minus V of x divided by x at x equal to 0.86. Oh no, I don't even have to write that. I can simply say this is true for all x in the channel. Okay, this is true for all x belonging to 0 through n. Now, since this is the case, I will just consider the case point at x equal to 0.86, which is the pinch off length that we found out. And at that point, I know V of x is Vgs minus Vt. Therefore, this implies Vds by L, which is now 1. So I will just write it as Vds. Okay, so L equal to 1 micron. So that is why this choice was made, because dividing by L is not required in many cases. Vds minus Vgs minus Vt divided by 0.86. So this implies yeah, Vgs minus Vt is equal to 1 minus 0.86 times Vds, and therefore now we know Vgs minus Vt is 4.3. So therefore Vds is equal to 4.3 divided by 1 minus 0.86 is 0.14, so 0.14. Yeah, so this gives us VDS is equal to 30 point approximately, or rather it's 30.7. So yeah, then you're right, it's 30.7 volts. So this is if it varies linearly. However, due to nonlinear effects, this current will kind of be arrived at a much shorter voltage, but nonetheless, it is going to be of the same order of magnitude. So that is what should be understood here. Like typically when we are talking about saturation voltages, it is going to be this high, and as you can see, for where were we? So did I calculate the current? Yes. So we are looking at. Oh, this is for a different problem, was it? Wait, I think I've made a small mistake. It is not 2.58. Oh God, yes. I'm sorry. I'm really sorry. This is 25.8. Yeah, I missed another factor of 10 because this would be, yes, there would be another zero here. Yeah, because that is 12 milliampere there. So this is 25.8. I'm really sorry. So I made a division error through and through. So this is 25.8 into 10 to the power minus 3. Therefore, that's 25.8 milliampere. Yes. So everything else, so here again it should have been 30 milliampere. Okay, so this again will be 25.8. So everything gets, so this is 25.8. Yeah, although I could have left it as 2.58 divided by 3. No, I'll just keep it like this to be clear. Okay, so now, yes. So ID sat is equal to, again here it is 30 milliampere. Now this makes sense. Okay, so to go from, so we found that at V equal to 1 volt, VDS equal to 1 volt, which we took to be the linear regime, we had a current of 12 milliampere flowing through the channel. Okay. And what we have found out is, yeah, 1.5 into 10 to the power minus 6. I did not take that number into consideration at all. So I just thought it was going to be 1.5 into 10 to the power minus 7. Okay, so yes. So now 30 milliampere is actually not that much. It's just 2.5 times. But what you can see is to achieve a 2.5 time increase in the current, the voltage is more or less increasing from 1 to 30 volts. So this is the idea of saturation. In the linear regime, had I doubled the voltage, the current should have doubled. And up until 25.8 milliampere, that will happen more or less. But the thing is, going from 25.8 to 30, which is a very small increase, the increase in VDS is going to be significantly large. Okay, so that is the idea of saturation. So this entire problem was done to emphasize that, or rather to show how the voltages and currents vary in a even a classical MOSFET. I shouldn't say classical MOSFET because even to observe like basic transistor effects, we have to uh, uh, reconcile with the quantum nature of matter. We cannot derive transistor behavior through purely classical means because even p-type and n-type materials cannot be defined without quantum mechanics. What I would say is a bulk MOSFET, so a macroscopic like a long channel bulk MOSFET shows this kind of a behavior. Now, this is kind of the pointer that we need. Now, why did we do all of this analysis? We did all of this analysis to kind of get an idea of what kind of behavior we need in our microscopic devices. Because the idea of using short channel devices is to increase the number of transistors in our, microprocessor, in our processors or any other device, digital devices. That is all. Other than that, their behavior needs to be more or less the same. Maybe we'll want them to work at a higher clock rate or something like that. But other than that, the switching behavior or saturation currents or the extent to which saturation occurs, all of these things need to be more or less the same. Okay, so I'm not writing this down because this is a point kind of outside of the purview of the course. But even though we are making small devices, like we are making nanoscale devices which leverage the quantum properties of matter, their behavior, insofar as voltage current relationship, should be more or less the same as bulk devices. Then and only then we'll be able to use them efficiently. So the reason why we did this entire set of problems in a physics of nanoscale devices course is to get a feeling as to how the voltages and currents ought to vary in a device. Now, using all of this info and this insight, we shall be looking at how to modify the existing or rather our currently understood designs of nanoscale devices, what more can be introduced or what changes can be made such that this kind of desired behavior is arrived at. Okay, so with that we enter our final topic for today's discussion, where we have to derive the expression for the unidirectional thermal velocity in a 2D ballistic channel. So what do we mean by unidirectional thermal velocity? So whenever we say thermal velocity, this is an average over energy. Okay. So what this, oh, not energy, it is energy. Oh, no. Yes. Energy. This implies this is kind of something like an integral v of e, some function of e. Let me not call it f of e because f is already being used as the Fermi distribution. So, like h of e dE. So this is what I mean by thermal velocity. There is some distribution function here. Okay, so there is some distribution function here. And we are multiplying velocity at that energy and kind of performing that integral from 0 through infinity. So that is going to give us the thermal velocity. Now what do we mean by unidirectional velocity? We are essentially concerned about the average velocity moving from source to drain. Okay, so that's what we like. Long and short of it, this is what unidirectional unidirectional velocity means. I want to see the average velocities with which electrons are moving from source to drain. This is what we have been doing in our study of the ballistic channels. So short channels. Okay, so uh, when I say unidirectional thermal velocity, we will represent it by this v plus of x. Again, x is the direction along which our channel is present. And this automatically implies this is an average over energy. And now the source drain thing, if you remember, for a 2D channel, we kind of took the angle at which it is entering and we integrated over all angles from say 0 to pi. So we took this theta and we did integral 0 to pi v of e comma theta d theta. We did this. Okay. So that is what we need here. We even did this for like a 2D, 3D channel where we had two angles, theta comma phi. That was solved in, I think, week 2 or 3. Like I can't exactly remember which. Please go back, you can see the videos or the slides. So this is averaged over energy and angle. That is why we have two angular traces. Like first one averaging, essentially I can also say that this is over theta and over e. Of course, but that is not required. So I will just say this is this. So what we have to do is we have to derive the unidirectional thermal velocity in a 2D ballistic channel. So now how do we go about this? What we know for a fact is that the energy depends strictly only on the magnitude of the velocity. It does not depend on the direction of the velocity. Therefore, these two averaging can be done independently of each other. So I will just put that out over here. slide. So first things first, since energy depends on magnitude of velocity and not the angle of approach, in the channel, the two averages can be calculated separately. Essentially, what I'm saying is this distribution function is separable. Like if I were to write v of theta comma e, then this is equal to sum a of theta times b of v. Okay. So when I want to perform the average, I can integrate this first and then integrate this, or rather not b of v, it is b of e. So yeah. So, so this is b of e. So it is a separable, like it's essentially variable separable. Okay. Like people who are familiar with some differential equations and things, like essentially if you want to solve something like the Poisson equation or even the Schrodinger equation for like multidimensional systems, we use solutions of this form. So this is essentially what is called a variable separable form, where the two variables of the function occur independently. Separable form. Okay. So now given that, what we have to do is first, let us say I want to do v plus with respect to theta. Now this has already been done. We know the answer is 2 by pi times v of e. This is known to us because we essentially integrate v cos theta. So this is, how did we get this from? We got this from integral 0 to pi v cos theta d theta. So we got this from this. Okay. So by, oh, of course, divided by integral 0 to pi cos theta d theta. Yes. And again, here this is not just d theta, this is v cos theta sin theta d theta. Yes. So this is where we get our is it or just 1 second? I'm sorry. I just got confused. Just 1 second here. No. Sin theta d theta is for the 3D system. Yes, that is where I made a mistake. So apologies. So yeah, it is just this. And over here, it's not cos theta d theta, it is, yes, that is where I made a mistake. This is just integral d theta. Yes. Theta, yes. And over here, it is going to be cos theta d theta. So this will be giving me a factor of 2 or minus 2 in this case, and 0 to pi, right? Oh, if I'm taking it as v cos theta, then the angle will also vary, not from 0 to pi, but from minus pi by 2 to pi by 2. Yes. Otherwise, it will be v sin theta. Yes, minus pi, so minus pi by 2 to pi by 2. Yes, now this will work well. Yes, so we do this. Okay, so this will give us this quantity 2 by pi VFE. Okay, so now we have to do the double average. Yeah, since I've already put the plus here, I didn't have to give the theta, but it doesn't matter. So now what we have to do is we have to integrate with respect to the energy. Now for energy, what we have to remember is the energy distribution is not only given by the Fermi distribution function, but we will also have to take into consideration the density of states. Okay, so first and foremost, I will write this as 2 by pi. Now V of E is simply going to be written as 2E by m star whole power half into uh, so density of states is going to be m star by pi h bar squared into the Fermi distribution function, which is I need not write it as f of e. So this is 1 divided by 1 plus e to the power e minus ef divided by kBt dE. So this is what needs to be written here. Now, when I say E here, it is understood that the this is with respect to some zero energy level. So typically E zero, like the zero energy level, may be considered as the edge of the conduction band. Sorry, just 1 second. Let me have a drink of water. Yeah. So now again here, this integral is from 0 to infinity, and again in the bottom we will integrate from 0 to infinity of the velocity part will be gone. So we'll just have m star divided by pi h bar squared into here I'm just going to write f of e dE because I kind of ran out of space. Okay, so now yes, so the double average velocity v plus x is going to be integral 0 to infinity. Now what we can see is these two quantities are kind of constant, so they will slash each other out, and only f of e dE will be here. And we know 0 to infinity f of e dE is 1. So the denominator becomes unity through and through. Okay, so all we have to consider is the numerator now. Essentially the denominator will be just this quantity here, which is a constant, so these two will kind of cancel each other out. Okay, so I'm just going ahead and writing this quantity here. So this is going to be 2 by pi into 2e by m star per half into 1 by 1 plus e to the power e minus ef divided by kBt. So dE. All right. So now what do we do further? We shall do the following. I will take E by kBt to be quantity mu and EF by kBt to be quantity, oh no, I shouldn't say mu. Mu we have been using for mobility, so we shall use a different Greek alphabet. Let me say eta. Yes, eta is the thing that we were using before. is eta f. This implies since we are doing dE, dE is equal to kBt times d eta. Okay, so yeah, so now what we will have is, yeah, so this implies plus x is equal to integral 0 to infinity just 1 second. Oh no, it's nothing. Yeah, moving on. So now, yes, this is going to be, now dE is, d eta is this divided by kBt. So what I have to do is I'll have to multiply and divide by kBt. So that will give us 2 pi pi into 2e, yes, by m star per half into 1 by kBt into, now I'm just going to call this f of eta. Okay, so here I'm kind of differentiating it with our Fermi distribution, which is temperature dependent, to this new normalized quantity d eta. Now, of course, I can take kBt per half into this expression to get integral. So yeah, so I will, what I'm going to do is I'm going to take a root 2 here, a root pi here. You'll understand why I'm doing that. So yes, so, or rather let me just leave the constants as they are for now. So this is 2 pi pi into 2 by m star per half, or let me just bring the kBt factor also in here. M star times kBt per half. Now I will like re-expand this eta per half into 1 plus e to the power eta minus eta f d eta. Okay, again 0 to infinity. All right. Yes. So now if you remember the form of the Fermi integrals. So the form of Fermi integrals is given by, let me just verify that for a second. So the form of the Fermi integral is given by, just 1 second. Yeah, apologies. Yes. So what has to be remembered is our standard definition of the Fermi integrals has a factor of 2 by root pi. So what I would need is a 2 by root pi factor to appear out of this integral to write this as a Fermi integral. Okay. So that brings us to, so what I'm going to do finally is, let me reshare the screen. I forgot to do that. Yes. Yeah. So what I'm going to do is I'm going to take a 2 by root pi factor outside, and then oh, no. So what I'm going to do is I'm going to keep the 2 by root pi inside so that I can separate the two. So what we have is 2 by pi divided by m star kbt. Oh wait, where is the kbt in the denominator? Kbt will be in the numerator. Yes, because this will be eta times kbt. Yes, sorry. So yeah, so this will be, I should not have written that kbt itself. So this will be, yes, kbt here, and this will be written as eta times kbt. Yes, now everything corrects itself out. So over here, what I should have done is eta to the power half goes there, and what we will be left with is so d eta is this, so de is kbt times this, so I will bring the kbt inside. Yeah, so this will be kbt by m star, yes, whole power half. Now I need a 2 by root pi factor, so a root pi will be pulled into this. So finally we will have 2 kbt divided by pi m star whole power half multiplied by uh, this whole quantity, 2 by root pi integral 0 to infinity 2 by root pi 0 to infinity 1 plus oh, eta to the power half, not 1 plus eta to the power half divided by 1 plus e to the power eta minus eta f d eta. Now this whole quantity is f half. So this is the Fermi integral of order half. So this implies our unidirectional thermal velocity in a 2D channel will be given by, now we can see that the denominator also will be like 2 by root pi essentially, because that is the value of the Fermi integral. So yeah, like essentially we will have to write this as 1 by gamma plus 1. So the gamma plus 1 factor will be there for order half. That is why we have the 2 by root pi factor. So For Fermi integral of order 0, we will have gamma of 1, which is uh, n minus 1 factorial technically. So that is going to be 0 factorial, which is 1. So the denominator is going to be 1. So this whole quantity is 2 kBT by pi m star whole power half into half. So this is the thing for a 2D channel. The next question that was asked is, how will this change for a 3D channel? So we can go through the same derivation again. In fact, I encourage you to do that. So instead of this, we will have an integral with respect to theta and phi. In fact, that has been done in one of the previous uh, sessions. So you can just go back to those slides and lift the answer from that. What I will tell you is for a 3D channel, but one thing that will change is this. This constant factor that I mentioned will no longer be the case because density of states will now depend on the energy distribution. Not on the energy value, not energy distribution. The density of states will now depend on the energy values. Because of that, what we will have is we will have an e to the power half term over here and an e to the power half term already over here. Every other constant will still get cancelled out. So ultimately what we will be left with is a Fermi integral of order half in the denominator and a Fermi integral of order 3 by 2 in the numerator, or rather order 1 in the numerator, not 3 by 2. And what I'm going to tell you is this. You can in fact work it out and find out that this is 2D, right? So right off the bat, we will know that only a change in the Fermi integral is going to happen. What more I'm going to tell is the following. By pi m star, I'm going to have the same factor, whole power half into, now instead of f half, we are going to have f1 divided by f half. So that is what is going to change when we go from a 2D channel to a 3D channel. You can work it out and find out. Now this quantity here, the slides of course mention it as the below threshold, or rather below saturation thermal velocity. However, this is also the classical thermal velocity. So how do we get the classical thermal velocity? Instead of assuming the Fermi distribution, we will take the Maxwell-Boltzmann distribution and just integrate to uh, do the same integration process as before. So if we take the Maxwell-Boltzmann distribution, so this is also the classical thermal velocity. I will just give a brief sketch of it. So classically, let me assume I just want to do Vx plus. So let me assume I found out what Vx plus is. So that is going to be so this quantity will be nothing but integral 2 by pi Vx, Vx varying from 0 to infinity, and our distribution function, Maxwell-Boltzmann distribution function, is nothing but e to the power minus, like it's going to be e minus e by kBt. Now e is going to be mv squared by 2. So this is going to be m star v squared by 2 kBt dv. So this is the distribution, and this for the velocity is a Gaussian distribution. So from this we can like split it into 3 independent Gaussians for Vx, Vy and Vz, and of course denominator factor will also be the same, 0 to infinity, not the same. It's going to be e to the power minus m star v squared by 2 kBt dv, not to the dv. Okay, now in this case, what we will see is that because of the properties of the Gaussian integrals, where this integral is essentially 1 by root 2 pi, or no, it will be root 2 pi. So using that property, what we can do is we'll just like split it out in terms of the different variables. So v squared is equal to vx squared plus vy squared plus vz squared. So we'll have to remember this. So this is just separate. This is not for the problem that we had discussed. So this is the classical case. So if that is done, then we can find out that we will get this same expression for the thermal velocity. Okay. So this is the expression for the thermal velocity. Whenever you're asked to calculate it, just go ahead, substitute the values into this expression and get the answer. So with that, yeah, I think we can conclude today's session. A note regarding the assignment questions. If you have any doubts regarding the questions for week 9, do consider referring to the notes slash video from week 8, because some of the questions carry over the concepts from there. So remember that the week 9 assignment contains questions from both of these weeks. If you are able to go through both of these discussion sessions, you should be able to answer more or less all the questions. So I thank you all for listening. We shall meet again same time next week. Thank you.